Once you settle in, we're going to get started with our next presentation. Well, again, thank you guys for coming today. Our second presenter of the day is somebody I reached out to, Brad Woods from the Virtual Foundry. I think a common request we've gotten over the years, right, is everybody wants to 3D print metal parts, but everybody wants to 3D print them at a much lower cost than you can do DMLS. And so, some of the barriers have been hardware to be able to do that, materials, et cetera. And I think Brad's here to share with us some opportunities to maybe make our hopes come true. So, Brad, I'll let you take it away.
Hi, I'm Brad Woods, the founder, CEO of the Virtual Foundry. My presentation might be a little different than most. This isn't well thought out. This is actually a project I started in my basement in 2014. And I was working with different methods of creating inexpensive ways of creating sculpture. What grew out of it was a powdered metallurgy strategy that I figured out a way to turn into a 3D printing material. I also have a little bit of a cold. I'm kind of winded, so bear with. What wound up happening? So I put this on Kickstarter. That's how I raised the first $30,000 that financed me out of the basement. And something unexpected happened, and that's that aerospace saw what I was doing and realized that this had broader applications than just sculpture. I was invited to Lockheed Martin, and this was a highlight in any nerd's life. I got to speak in the Hubble Auditorium to a gathering of their engineers. I don't know how I will top that, but I'll try. So this gave me the motivation to go bigger. And what we've done, the Virtual Foundry is a materials company, period. Anything that we sell on our website that's related are just value adds. And when I first started selling only the filament, people's first question was, what hardware do I buy? So we just started making the hardware available. And this approach has also evolved over time. The first ones, this guy. So the owl, this was printed on a printer bot simple made with zip ties and plywood. Not sure if I can pause these, but that's okay. So I was literally printing and sintering until the moment I had to get on an airplane to go to Lockheed Martin. And that's the part I came up with at in a stroke of luck at the very last moment. Beyond that, the premise is very simple. It is sinterable material. My personal opinion is that people are striving for one-click metal. And we'll get there, but in the meantime, there's a lot of things that we can do that are very helpful and will move the technology forward without waiting for companies like Trump to come up with a solution that everyone can just hit print and go, the easy button. That's what the Virtual Foundry does. We've done this with about 40 different materials. We'll take powdered metal, glass, and ceramic, blend it with our polymer, and make it into filament. That's it. That's our whole business model. It's open. We don't make a printer. We don't make the kilns that you need to process it. None of that. It's very simple and wide open. I used to try to get the word democratizing 3D metal to catch on, and it did not, but lately it's starting to get a little bit more traction. So this is a completely open platform. You can buy our materials. They'll print on any printer. It doesn't matter. You can sinter it in any kiln that has a programmable controller. And these are inexpensive. The lowest cost one that we sell on our website is under $2,000. With that piece of equipment, and even the lowest end Bamboo Lab printer, you will have metal parts within a day or two. We encourage people to start with bronze and copper, simply because they're the absolute easiest to work with. They sinter at relatively low temperatures. Yeah, I need a drink. They sinter at relatively low temperatures. They're easy on the kiln. They're easy to print, and it's just easy to work with. Let's see if I can pause these. So this is a close-up picture of the filament itself. And when you look at it, you can see that you don't see any plastic, you see metal. So there's just enough plastic in it to bind the metal particles together. So, like I said, this is what the filament looks like under a microscope. And it's just that simple. It's just powdered metal bound together with a little bit of PLA. Early challenges were getting a filament that was strong enough to be able to work with so that you could get it into your 3D printer without it breaking and such. I worked that out. And as time passed, scaling up. So we'll now run, in a single run, we'll do 200 pounds of material. It's gotten very easy to make. We've refined the manufacturing process. The price of the materials that we sell is purely based on the cost of the powder itself. We'll come back to that. We have resellers all over the world. We're up to 4 or 5 resellers. Filament to Print is in Spain. They've been a very good partner for us. This is a piece of 316 printed and sintered. The key limiting factor in the quality of the print is the printer. So it's the capability of the printer itself. So we've had a game-changing event in the last couple of years, and that is Bamboo Lab. Their auto calibration technique using LiDAR works perfectly. So you put our material into their printer, it auto calibrates and prints. It's just that simple. Where in the past, it was a little bit more challenging. We worked with mostly Creality type printers. That's where we started. Flash Forge, things like that, very inexpensive printers. And they all work. And like I said, even the PrinterBot Simple from 2013, literally made out of zip ties and plywood, laser cut plywood, printed some of the pictures you see here. So as printing has improved, the output quality of our materials has improved along with it. And this is exactly what I was hoping would happen when I started this project. I decided to put no effort into the printing technology or the software behind it, nothing like that. We do nothing but materials, period. And we also do this on a custom basis. So people will say, hey, can you make this 3D printable for us? And We do. We've probably done 25 or 30 of these for just about anybody you can think of. The NASA JPL, National Labs, the Air Force is always coming up with new alloys that are interesting. So they come to us and say, can you make this into a filament? And the answer is yes. If they can supply it as a powder, we can make it into a filament that's 3D printable. Other strange examples. We make a moon dust simulant 3D printing filament. And it's exactly what it sounds like. And it turns out that in at least some places, the dust on the moon is sinterable. It has a really high iron content. So we took the dust, made it into filament, and you can sinter it into something with a fair amount of structural integrity. On that topic, people always ask me, what are the final properties of the piece? And I don't answer the question because it's so highly dependent on post-processing that I can give you guidelines. If you follow our recipes that are on our website, you'll get a good idea of where you'll land. But perfecting it for whatever your application is going to take a little bit of research. And that's kind of the point. We're not looking for the easy button. We're not looking for one-click metal. We just want to make this, it's more of a, I think of it more as an operating system. It's a platform for development, but it scales well, or at least as well as 3D printing will scale. I have some examples. We've done everything from micron scale, so nothing, up to, we can handle about 100 grit. I can't think of what that is in micrometers, probably about 90 or yeah, about 100 micrometers. So the spectrum is large with very few limitations. Yeah, there's one, but I can't think of it.
Offer support material?
No, just use PLA. It's inexpensive.
When it's sintering, how do you deal with any kind of, like I've seen some of your parts, I think you got copper cutlets here or something like that.
Right.
How do you keep the windows from folding in on itself when it's
We
being sintered, being processed in the kiln?
call it, we call it ballast. So we'll bury it in some type of material that has a little bit of mass to it. So all the support during the sintering process comes from the ballast material used during the sintering process. So overhangs are only an issue during printing, and you can use any support material you would use with any other PLA, or just use PLA. Okay. I'd like to mention, wait, Austin, what was the code? Austin is my right-hand man. So sometimes my demeanor is a little casual, but it's interesting when I start talking about our list of customers. It's everybody. So off the top of the list, Apple, Hewlett-Packard, Western Digital, NASA, actually 6 different places at NASA that we've worked with. Tesla, Intel, Microsoft, Xerox. Excuse me. Trek, actually, we did a few things with Trek. They're a good partner for us. Military, and this is all over the place too. The military has decided or figured out that they can print a shaped charge liner with our copper material, and it outperforms the ones that are machined. So they've driven a several gram cone of copper through as much as 8 inches of reinforced armor. And they just print, they don't sinter it either. They just print it, put it in with the C4 and blow it, blow it up. Army, Navy. Navy's interesting because they do a lot with nuclear power. So Newport News is a very good customer for us. They use our tungsten material as radiation shielding on board both submarines and aircraft carriers. There was a time, and this comes up every once in a while, where when you say 3D printing, people want to ask about guns. This has chilled out a little bit, but I think it's kind of coming back. So we consulted with the ATF. We built the system for them and installed it, showed them how to use it. So they can make, so the ATF can make their own gun parts. Department of Energy is huge. The national lab systems, we shipped to, I'd say about 13 of the 16 or 18 national labs. The most interesting one right now is the International Space Station. That's actually considered a national lab. And since our material prints in a printer that will work with plastic and sinters in a kiln that they already have on board, the Air Force has funded a research program to send the material up there and give it a try. Every university you can think of, Lockheed Martin, I mentioned that earlier, McDonnell Douglas, Mayo Clinic, Caterpillar, Canadian Nuclear Labs, and there is a brand name nuclear reactor, and I didn't know this was a thing. It's called the CANDU, and there are dozens of them around the world, but it's a Canadian product. And this is a good argument about cost and how it relates to 3D printing. Most people are trying to get their part cost down. That's not our focus. We focus on competing with the cost of time. And when you do it that way, it's priceless. So for example, the Canadian labs, they have hotspots. So they're circulating water through the, coolant through the reactor. And every once in a while, an atom or two will come loose and make it into the circulation system. And they have to shut down the rooms where they'll show up. And that's incredibly costly. So what they do now is they send in a Boston Dynamics dog robot with a radiation scanner on its head, and then go back and they'll use our tungsten material to print something that perfectly fits around wherever the radioactive particle has become lodged. I thought that was a cool one. And they're the, we normally sell this stuff in half kilos or a kilo. They asked us if we can make 5 kilo spools of this stuff. And it's very expensive. I think a 5 kilo spool is nearly $4,000, somewhere in there. But the cost is irrelevant when you compare it to taking a nuclear reactor offline. Cars, Toyota, we're at all, every car company. Recurring themes for us are green energy and CO2 capture. So we just dug into last week, we dug into a new carbon capture project with NASA that, and this stuff's purely, it's in its research stage. So I'm not saying this is going to happen. It's years out yet. But it would create a carbon neutral natural gas turbine for generating power. So they would simply capture the CO2 as quickly as they're producing it when it comes off of the energy turbines. Neutron shielding, we just released a new product, boron carbide, and its only purpose is to knock down or take the energy away from a floating neutron. We've done custom materials that are used in supercapacitors, thermoelectric devices. This was one of my favorites. So as a research project, these people built a Peltier device. So if you have a difference in heat, it's cold here and hot here, you can turn it into electricity generate directly using a Peltier device. They call them thermoelectric energy generators. And so these guys had us print two different versions of their material, one doped positive and one doped negative. And they made giant thermoelectric generators, and they just placed them around geological hotspots. And it just sits there and produces energy. It's brilliant. Texas A&M, we work with them. Rice University came up with a way of creating low-cost graphene at scale. So we're working with them to come up with better conductive materials. And I found that if I just take our regular copper and add trace amounts of graphene, it will conduct electricity infinitely better. Not literally infinitely, but many, many times better, to the point where it will outperform any of the electrically conductive 3D printing filaments that are currently on the market. And in most cases, our customers are looking for a solution to a problem. So it can be magnetic. So we make highly magnetic materials also. I have some examples over here that, I mean, it's hard to even get to peel a neodymium magnet off of this 3D print. Yeah, I'm not going to talk about them. The Ice Cube project in the Antarctic, we made them a drill bit. So internal cavities are difficult to machine, but they're very easy to 3D print. So we made a series of drill bits for them that make these 4-inch holes in the ice. And really it's just a heat sink. They run boiling hot water down to it and then bring the liquid water back up. So yeah, they tried forever to get a good way to do this. And we were able to 3D print it in 2 days. It's just very, very simple. I talked about graphene, uranium. Okay. There are actually many applications for 3D printed uranium. And obviously that's not going to come back to our shop where we manufacture it. So we've done a series of uranium simulants where the engineers believe that that'll be close enough that they can do their experiments. And then later we'll come in and we'll help them figure out a way to make it into a printing material. And most of this comes from recycling. There's a lot of waste. There's a lot of waste material in the fuel for nuclear reactors. That's a Department of Energy project. I think that about covers it. We have some parts over here. There's some floating around. Can I answer any questions? Right. Right. So the easiest ones are bronze and copper, like I mentioned. But it'll sinter clay, glass, anything. Humans have been sintering things for 3,000 years. I mean, it goes back to pottery. And this is exactly the same technology. The only difference is how we form the part. The kilns that we sell on our website, we're a reseller for Neighbortherm. They're a huge German company that makes every kind of sintering kiln you can think of for industry and commercial applications. So if your application is large, we'll send you through to them. If it's simple prototyping, we sell these kilns that were originally meant for hobbyists or school art classes, things like that. That's why they're so inexpensive. The only thing that the kiln needs to get hot enough, obviously, for whatever material you're sintering. So stainless typically is about 2250 Fahrenheit. And the kilns that we sell will do that, and they cost under $2,000. But you're kind of running it at the high end of its capacity. It's not going to last very long. If you're going to do that at any kind of scale, we would refer you to Neighbor Therm, and then they would help you out. We're working on this, and we have a couple, and this is actually just a decision we made recently. We're going to add this as a service to our customers. So we'll take customer parts and sinter them. We've been doing this on a test case basis, and it's going pretty well, so we'll keep going. Yeah. Are you talking about the extruder kit? Right. If it's a hardened steel nozzle, you're set. So we sell the hardened steel nozzle for the bamboo. No, they last years. I mean, we've had some that last forever, as long as it's hardened steel. And it varies from material to material. Our most abrasive is tungsten. If you really try, you can grind one off pretty quickly, but that's a printing error. It's when the nozzle is too close to the previous layer and you're literally scrubbing it on there. Yeah. Yeah, we brought in its green state, I assume you're asking, so there's still plastic in it. I'm comfortable saying shockingly strong. Everybody thinks that it's going to be weak, but it's just not. And we have some green parts over here. You can come over and try to break if you'd like. Right. Brill has been a factor that we've wrestled with since day one. But I believe we now have it under control. So our test case is fold it into a loop. How tight can you pull the loop before the material breaks? And additionally, we came up with a gadget that pre-warms the filament as it comes off the spool. Yeah, most of the breakage during printing is that when it sits on the spool, it develops that circular memory. So you're literally bending against it as you're trying to print. So we have this thing called the filiwarmer, and it just removes that memory from the material as it comes off the spool. Yeah. This is user dependent. You can go anywhere from 15% porous to about 98% solid. The theoretical max at this point seems to be about 98, but people keep getting better at it. Each time somebody asks me a very specific question about the properties of the final product, I'm going to refer you to scholar.google.com. We've had great success with universities all over the world picking up our materials and doing this type of research. And it's beyond anything we could possibly do internally. So if you have a question, there's likely a paper written about it. At last count, about 125 published papers reference the Virtual Foundry by name. Yes. We did a deep dive on gem nozzles, Austin. with the gem nozzles, they don't necessarily wear. They'll eventually chip or something like that. So they're not necessarily grinding off the ruby, but they become unusable for a variety of reasons. Yeah. We're working with those guys. We'll get back to you on that. So this is also completely process dependent. If you want your part to be completely dense or as dense as theoretically possible, it will have shrunk by 17%. And these are numbers that are very normal in metal injection molding or the two companies that I used to have a problem with, but they've kind of faded away, Desktop Metal and Mark Forged. The shrink rates are about the same. Yeah. The heaviest piece that I've done, it weighed 6 pounds. It was a 6-pound copper piece, and that worked well. But on the upside of size and scale, it's user dependent and your tolerance for experimentation. Yeah. Okay, so one thing with DMLS has a massive problem with inherent strain, like internal strain will later crack, things like that. One of the advantages here with our strategy is that you're heating the whole part at once and you're cooling the whole part at once. The challenge is that the part will shrink if you want it densified. So you have to figure out a way to cope with thin spots or something that's prone to cracking during densification. So it's all trade-offs. Yeah. It doesn't warp. And at first this was kind of curious, but we realized that there's almost no plastic in it. So there's no place for the plastic to shrink. So bed adhesion, where other materials struggle to adhere, we have the other problem. If you accidentally print on a piece of glass without laying down something as a release agent, your print bed is dead. It won't come off. So we have incredible adhesion, though I can't explain why. And that adhesion lends to fewer problems with warping and yeah. So where we want people to start is bronze or copper, just because it's easy. You'll get a quick victory. I know they're not massively popular in industry, but it's a good way to get your feet wet and understand what's going on at minimal cost. And a kilo of bronze cost? About 130-ish, somewhere in there. Somewhere in there. About $125 or so per kilo for copper and bronze. And then it kind of goes up from there. One note, and this comes up, active metals are incredibly difficult to sinter. So like magnesium, titanium, and aluminum, very difficult. Sintering them is a completely different beast. We sell them, but we don't even provide recommendation. We can tell people how to debind it. It all works the same, but we don't know how to sinter it. It needs a shield gas. It needs, in some cases, it needs hydrogen in the atmosphere. So people do it, but don't start there. Yeah. Yeah, exactly. We recommend that you use a 0.6 nozzle. You can print with a smaller nozzle, but you'll clog more frequently. So 0.6, nice and stable. But no, you can switch back and forth all day long. It is PLA. It functions like PLA. When you go to set up your first slicing program, set up for PLA. Exaggerate the flow rate a little bit, 125%, so quite a lot actually, but that's it. The rest of the parameters are PLA. Yep. Yeah. Yeah, ramp rates. Ramp and hold is what you're looking for. So you can raise the temperature at a very specific rate. All of our materials are debound with heat. There's no solvents involved or anything like that. Everything goes to a vapor. So, right, so no leftover chemicals, which is nice. And but you have to ramp it at a very specific rate to keep it from warping or changing. Yeah. It's kind of a long story. and, actually, it's about 5 years old. That isn't pure 316L. It's 316L, but it's infused with bronze. So there's also no porosity. Theoretically, no. I'm sure you can find some. But, and this is very common in binder jetting, where they'll infuse the parts with a secondary material with a lower melting point. It's called liquid phase sintering, and all those tools apply here. So nearly any of the pieces you look at have flaws, and I consciously decided to just put it out there. These are things that can be overcome with some skill and some patience, but it's going to take a little patience. We have a piece, I don't know if it's going around, it's a little cup that is one print wide. Right. Then, well, then you just got to be more patient. You can remove you have to get the plastic out of there. It's not going to work. And the bigger the piece is and the more plastic you have to remove, the more time it's going to take. And the further that plastic is from an outside surface, that's also challenging. It can be done, but just slowly.
How thick is the thickest piece you've done? At what point does it start becoming a game of patience and challenge? And of what, is 1/4 inch a nice, easy chip shot?
Yeah.
Or is a 1/2 inch become a challenging?
No, it doesn't start to become a problem until probably 3/4 of an inch. And I mean 3/4 of an inch from a surface. Yeah. Yeah. Only during the debind. Well, that's debatable also, but mostly during the debind. If you hurry the process, rather than the binder material sublimates, it goes from a solid to a gas. But if you don't give it enough time, it doesn't just sublimate, it will boil. And if you boil the binder, then you have the obvious problems, porosity and distortion. Yeah. Yeah, you put it in there, and these are programmable kiln controllers. So you put it in the kiln and you bury it in a ballast during debind and set it to ramp at 150 degrees Fahrenheit per hour till it hits 900 degrees, hold 3 hours. And that's it. That's the full debind cycle. Yeah. Great question. This is kind of one of our innovations. We use charcoal. So at 900 during the debind, that isn't hot enough to oxidize most materials. It could be problematic somewhere, but in a very baseline way, it isn't destructive. It's hot enough to burn off residual carbon, but not burn off, sorry, I lost my train of thought. But right, we bury it in activated carbon, and the activated carbon will react with any present oxygen. And we've tested this all the way up to 316L. And the L is for low carbon, and it continued to be low carbon even after this process. I can't fully understand why.
People are interested in finding out, like, we have a bamboo printer now, and it's a range. Check them out with the guys. What you do? Right.
Yeah, and we're also, we consult, we'll work with you and get you through, we'll get you going. Every one of our customers, we have open access to the tech side of us. So we'll consult on your projects too and make sure you're going in the right direction. Yeah. Right. Mm. If your goal is just a metal part, you know, copper or bronze, everyone will succeed. If you buy copper and bronze and print it and sinter it, you will succeed. They get more complex when you get into the stainless, the temperatures go higher, some of the parameters get a little more challenging. But they're not as challenging after you succeeded with the copper and bronze. So we ask people to start there. Well, our fastest growing segment right now is schools. So grade schools and high schools. And if they can do it, I think everybody can. We do not. It's not worth it. We went through the evaluation process with Ultimaker a few years ago. It was brutal, and we made it into their library, but it really wasn't helpful to us as a business. And we decided not to do that. I will say, pick a generic PLA and go. Yep. Yeah, and the Bamboo Labs have such an impressive auto calibration that it just works. Yeah. Uh, I don't know yet. I think it's probably the best answer. We have a lot of people that run IDEX machines, so they'll just, you know, so then it's a different head. But I don't have a good answer to that question. We have the equipment to test it. We haven't gotten to it yet. Yep. Right.
A lot of the nowadays crazy fast, especially with PLA and big print.
Yeah.
Do you actually print at those speeds, or do you like half the speeds, like.
Yeah, actually, that's a good question for Austin. What do you think about speeds on the Bamboo Labs with our materials? Yeah. Yeah, it's very viscous, so it takes a little more time to extrude. So if you exaggerate that, it balances itself out. Yep. Oh, with the bed slingers? Definitely. Yeah. But it depends on how big the piece is and how far it is off the plate. Right. It's all about the Z. You start getting a, top heavy, that's a different problem. So yeah, definitely there. But even with the bamboo, like I think their experimental mode is ludicrous. You can print our stuff in ludicrous. It won't look great, but you can do it. Yeah. Yes. Yeah. Yeah. Yeah, and we've ordered that equipment. I think we'll come up with some kind of a strategy that will work with our spools. But you're right, our spools are bigger, and it's all about the circular memory problem that I was talking about earlier. We're able to get the metal content higher with the larger barrel size in the spool. Yeah. I think it would probably break it. The warmer that I'm talking about, it's nothing special. It has a static thermostat in it that heats to about 60 C. And it naturally oscillates but yeah. Yeah. Yeah, there's a group at Harvard that's trying something similar. Right. So, right. Right. So they're trying to figure out how to lay it down just like an FDM, but follow it with a sintering laser. So yeah. Right. We're exposed to hundreds of projects, and these things just pop up all over the place. And it's kind of strange. I used to get disappointed when they would die off, but I don't anymore because they pop back up later. Somebody will pick up the ball and run a little bit further. Yeah, yeah. Feel free to ask questions and come on over. We have some more parts at the table too.